recording just in case, and it is 4 p.m. First of all, before I even talk about anything technical, thank you for being here. Thank you for sort of, I guess, joining me on this journey because I remember probably in year one just hearing about this, I don't know, some random place on YouTube, and it was just astounding. But when you actually get your hands dirty, when you actually try to mess around with the math, it gets even more intuitive. It gets even more, beautiful. And that's what I felt when I was sort of dealing with Noether's theorem. And I'm just going to try to convey a sense of that uh, through these discussions. So in general, what I'm trying to give you guys is answers to, obviously we'll be covering analytical mechanics from the ground up. Uh, we will certainly be doing that, and that will in fact require us to, unlike usual treatments of analytical mechanics, we would need to define what is a vector space before we even talk about mechanics and so on. We'll see what that holds. And when I say analytical mechanics, uh, I would sort of throw in Lagrangians, your Hamiltonian formalism, and also Hamilton-Jacobi theory, and why it's useful and what why we use it. Um, and I'm hoping to probably, in terms of math, we will dive into basic what's called abstract algebra, which to again expand this out, vector spaces, uh, and why we use certain types of vector spaces, um, and groups, and why we use certain groups. What do they mean physically as well? And along this way, you'll probably also encounter some objects that interweave these two, such as tensors and dual spaces and so on. Although they do sort of come under the definition of these two. And we will be looking into a little bit of field theory towards the middle of it, and we will also probably dip our toes a little bit into gauge theory to get an idea of what the hell this word means. Why do people think it's important? Why do people think it's not important? Because it's still kind of up in the air as to, do we really, is it a redundancy or not? Um, and whenever we talk about any of these things, whenever we introduce any of these, we will be dealing with several examples. Examples to be specific will be thrown in from, I'd say, classical mechanics, QM, and also a little bit of field theory. The C here stands for classical, not conformal, please. Um, so yeah, and maybe since the book that we've chosen is kind of really, it's a rather wide one, we might even encounter examples from economics at times. Uh, so this is, and what I'm trying to set up this sort of knowledge base and try to show you guys how it all comes under one theorem, which is Noether's first theorem, uh, as stated, and how that is so useful in all of these things, and how that underpins modern physics as we know it. And as a brief flow of topics, this is how I'm thinking of doing it over the next couple of weeks. Um, I am in my senior year, so might be a bit irregular, but I'm gonna try to be as active as I can. Probably a lecture a week, or sometimes even two a week. But this is what I've sort of planned out as a sketch. This is the flow of topics in the book as well. So I'll show you guys the book at the very end. I'm following it pretty strongly, you could say, and we're going to look at functionals today. Um, and the rest will follow through. But more importantly, uh, before we even get started on anything, uh, I thought about how I should be going about this whole thing. And what I thought was, I mean, this could be a reading project, this could be a discussion group, whatever. And I don't want to keep this as a monologue because I'm not very good at it. First things first. Um, but I would love to see you guys come up with comments or questions at the very middle. Please do. All right. But more importantly, I would love to see you guys crack down problems from the book, because the end of chapter section, or as I call it, end of chapter section, whatever. It's of two types. So it has reflective questions, which sort of tie into the physics and the bigger picture as well. And they're kind of, how do I put it? They're deep thought kind of questions. They make you want to ponder and actually maybe look through your second or first year books and try to figure out what the hell's happening. And then there are numerical problems, of course. And for both of them, I would say they tie pretty well with the appendices in the book. They have a good coverage of a decent amount of physics and math. So from what I saw, there was a bit of analytical mechanics there, some bit of special relativity, and tensors were also being loosely defined there. So I'd love to see this happen. Anyways, I will be, every week after our session, I will maybe given a day or two later, I will put up what I've come up with as solutions to these sections in the book, and we can go over that as well. So this is what I was thinking of in terms of pedagogy. Uh, you know, if you guys have any comments or so, you can jump in. Okay. In that case, let me get started on what we're trying to do today. Today, I want to define these words. And when I say define, I'm going to define certain things with an equal to sign. And I'm going to define certain things in a rather, how do I put it, rather in a very intuitive sort of a fashion in a different sense. But this is the way I understood it, and I think it helps. But if you think there's a better way, please stop me in the middle and do jump in for comments. So I'm going to spend some time on this section first. These words, what the hell do they mean? And I'm also going to talk about a continuous and discrete transformation for a bit. Um, and I'm going to state Noether's theorem, Noether's first theorem, loosely based on these words. Um, Not technically, because the technical development would need us to define groups and so on. But nevertheless, it's a good approximation of what was actually said by Noether. And also on a side note, we're not going to be deriving things the way uh, Noether herself derived it or proved it. We're going to be using something called the Run-Trotman identity, which, from what I can tell, is much easier, less algebraic approach. But nevertheless, sometime if we do find time, we'll sort of visit the original paper and we'll see how that goes. But anyways, let me get started. Um, uh, First of all, this whole concept of invariance. We have probably encountered invariance when it comes to rotations. Mostly when let's say you commit an action and it doesn't change. For example, you rotate uh, your coordinate system, but in Euclidean space, but the length, the norm of your vector or your object does not change. So this property is invariance. So invariance is it's sort of like not changing, um, and um, the, and you can even say that it's invariant because it's a scalar in a sense. That's true as well. So symmetry is a little bit more subtle than that. So symmetry is the invariance of a particular object under a particular transformation. So again, we can talk about rotations here. When you rotate the object in space, its length is not changing. And that's kind of how rotations are defined. They're defined as isometries, or fancy math word for things that don't change your length. So this is what symmetry means. And then we can talk about what I would call passive and active transformations. And so if this is your system, for the lack of a better word, and I have a ruler here, or this is my coordinate system for describing this system, the transformation of the coordinate system, the transformation of the ruler, of the measuring scale that I have, the change in that is what I would term as passive, and actually making a change to the system in question without making a change to the coordinate system is termed as active. And throughout this whole discussion, whenever I say transformation, I will be talking about passive transformations. And they're strongly correlated to physics, and especially when you go to places like GR, you'll see that you kind of do define space and so on, things like that based on passive transformations. Um, and then there are global and local transformations. These are some fun images, but TLDR, a local transformation is a transformation in which you make, the same transformation is applied to every single object in the system. Um, Whereas a local transformation is a transformation that's applied to a subsystem. So it needs to be localized and it needs to be defined in terms of coordinates. So this is the distinction between global and local transformations. And this is where things get interesting when you're trying to consider, um, one second, um, whoops, yeah, continuous versus discrete uh, transformations. Um, so obviously, what is continuous without referencing topology or something incredibly more rigorous in a sense is a thing is continuous if it can be built up in terms of infinitesimal quantities. That's all there is to it. And we can sort of define this as, so let's say I have a transformation g of theta, and I define it to be a very small increment, okay, a very, very small increment from the identity. So this is something that's less than, it's less than 1, or it's less than 0.1. It's a very, very tiny number times this being my change. And for the lack of a better word, which I will define later on, I'm just going to call it a generator. And this word does have some significance, mind you, but we will talk about it later. But let's just call X the generator for now. And I can actually define this in terms of my parameter theta of the function. And I'm just going to sort of switch things up. And if my g can, oops, yeah, if my g can take any arbitrary theta as an input, that would mean that n is a pretty large number. Okay, so just keep that in the back of your head. Um, now the question we can ask is, this is a very small displacement from the identity, and can we actually construct a finite or a more solid change that uh, you know that doesn't involve something such a tiny displacement from the identity? And you can think of this probably as being a rotation. So I'm here, this identity leaves, oops, yeah, this identity is just going to leave my arrow hanging here, but I have a very, very, very small change. is moving it here. And please, image is not to scale. So this is what I'm considering. So this is the very, very small change. Now the question is, can I build up a sizable change out of very, very small changes? And if the answer to that is yes, then you have a continuous transformation. If not, then you would need to consider discrete transformation. And the reason is because, as I said earlier, transformation is continuous. Um, if and only if I can sort of sum up, this is a very loose math notation, not to be taken seriously. If I can sum up or heck multiply up very small infinitesimal quantities, and that actually pops into something finite and tangible. And in this case, I can actually show you guys that um, this does turn into something else. So if I consider a function h of theta that I will call g of theta to the power n, this would actually be something along the lines of this. And as a very naive example, if I take this limit of n to go to infinity, oops, I forgot the generator. Yes, to go to infinity, I would if I just pop in the limit, um, then it's kind of obvious that it does turn into something like this. Maybe I'll show you guys later how this pops up, but it does pop up. And this is a rotation, yes, and it's obviously going to be tangible because, as we've seen, e power I theta does cause rotations. Again, I'm using analogies here, but just to give you a sense, this can be a finite term, mostly because e power whatever can be expressed as a Taylor expansion, and the leading term in this case would have to be 1, and this would end up being greater than 1. And if you're wondering how the heck do I, x can be a matrix, and how the heck do I exponentiate it, and there's really no frustration there. All I would have to do is just Taylor expand. And yes, there are some issues with respect to convergence and so on, but um, again, we'll be dealing with that later. So this is a distinction between continuous versus uh, discrete transformations. And there is so this is all that I had to, before I go anywhere else, this is all that I had to say about transformations. So if you guys want to cut in and ask questions or comments, please feel free to, or for the lack of a better, criticize my terrible math skills, please do. Is someone saying something? Yes. um I'm sorry, but your voice seems a little broken. Is anyone else able to hear what they're saying? Shush. Can you possibly type it out then? Nah, it's okay. Please. It's okay, man. Okay. Um. Okay, I guess we'll shove it towards the end. Or if you'd like to, we can. Okay, you're typing. All right. Perfect. Um. Um. Okay, so we've talked a bit about transformations. We've defined a bunch of words. Um. So now I'm gonna talk to you guys about something that's a little different. I'm gonna talk to you guys about something called the conserved current, and um, it's a rather weird term because, well, what is current doing here, um, and why is it being? What do you mean by the whole idea of being conserved? But a very naive example that you can possibly take would be, um, I guess, your probability density in quantum mechanics, and this is one way to write it. There are, obviously you can write it in bracket, but I'm just going to keep it to this notation. And in some scenarios, you get something like this. And this is what is referred to as a continuity equation, where your this quantity, its derivative with respect to time is going to zero, and this is called the continuity equation, and the object that follows this is simply called the conserved current. That's it. There's nothing more, nothing less to it. But there are some subtleties that we'll slowly cover, and maybe some more examples from E&M and so on. But now we're sort of ready to actually state what Noether's theorem is about.
I'm sorry that I have a remark here. I think
Yeah, sure, sure. Yeah, yeah, it is minus dou of j. Yes, 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 yes. I just said some scenarios. I put it in a loose context. Yes.
all right. Yeah.
But yes, as our prophet was saying, whoops, yeah. So this in general is a little bit more wonkier. I chose a rather more simpler case, but this is what would usually pop up in Q&M.
Yes, and uh, problem that it was not because
Mm, mm, yeah. And do you remember what this object is? Because it's 2 h bar I m. It's something like, wait a second. I don't exactly remember. There's a constant something here, minus psi dou psi. It's this is right, and there's some, I don't know what's in the front, but there's mass.
I think it's I think
Oh yeah, it's h bar over 2 mi. Yes. So this is j. This is how j is defined. But yeah, anything else?
no, it was just this remark.
Okay,
It's fine.
all right. And yeah, we can actually state what Noether's theorem is in a loose sense. So every differentiable, I'm going to underline these words, symmetry of the action of a physical system has a corresponding conservation law. So in first look, it's just, this is usually what goes around. There's something like this. But again, your symmetry has to be a little bit more specific. And when I say differentiable, it implies that the transformations involved have to be continuous ones. And when the word action is used, it's a little bit, okay, I don't know how many people here have seen Lagrangian mechanics, but the action is a it's a functional, as we'll see later on, but it's something defined as the time integral of a Lagrangian, or the in field theories it's the for integral of a Lagrangian density and so on. But essentially, this is what the action is, and usually in physics in general, you're to look at your path or the path taken by the object or the equation of motion, you would usually take this integral and quote unquote extremize it, or some people say minimize it. And the result of extremizing would just be it's just taking the derivative of s with respect to a parameter. Where you can parameterize L here, and then you take the derivative of it, and you equate it to zero and solve for it. That's that. You're essentially what you're doing is you're finding stationary points. So if your S is a curve, you're trying to find the stationary points of that curve. And when you do try to do that, the equations of motion pop out. And this is primarily due to this guy called Hamilton, who said that every physical system uh, follows the minimization principle, t minus v integral dt. You minimize this, you get the equations of motion, and this turned into Lagrangian mechanics. And the T here is kinetic energy and V is potential energy. And again, this is only something that holds for um, systems that don't lose energy over time, systems that are rather closed. But as we'll see, there's a more general way to define this later on that we will pop out. But for our sake, the action is just a, you don't need to bother about any of this for now. You can just think of the action as a functional, which we will define properly in a moment or two. Of that is related to a physical system. So one where so it's variables must be the same variables that you would use to characterize the coordinate system of a uh, physically relevant thing. So it could be position, momentum, or velocity, and time, and so on. Okay. Um, but let me get to this bit. And conservation law, as we saw, is nothing but there's a conserved current. So a bit more, I say fancier way of stating this is that for every continuous symmetry of this action functional of a system, there is a corresponding conserved current, is how you could state Noether's theorem. But again, this does not get to the subtlety of it, and it is going to take some more of math to sort of unearth this, and especially this extremization thing. It is very simple in when you're considering just an f of x or something like that. It's just the first derivative. But when you're talking about something multidimensional and something that's defined inside an integral, things get a little trickier, and you do need to set your bounds on what is relevant and what is not relevant. We'll see that soon, and maybe during the Q&A we can talk a bit about how it pops up as well. But now I'm just going to define what a functional is. I'm going to, in a loose sense, first give you guys a few examples, and then actually get to how it's defined, and how we are only concerned with a very special case of it. Okay, so a functional in general, we would use the letter J, is a map from a set of quote unquote well defined, which is to say, later on this feature would be relevant when we're talking about derivatives of these functions and so on. But for now, just functions, it's just a map. It's a machine. You can think of J as a machine that takes in a function x of t or so and spits out a real number. So this is all that I would say about a function at the very starting point. And some examples that we have probably seen earlier on is first and foremost the length. Um, so or slash distance. In Euclidean space, you would define it as the integral over ds, and you sort of switch around things. You can talk about ds as simply being the square root of uh, some of these two integrals. Yeah, and you again, this is a very 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 naive way of playing around with this, and it might be comical in a lot of senses, but for our sake, you can sort of play around with this and end up with this, as we've seen in Calc 1. And all this is doing, in a sense, is this is what it's taking as an input, and the resultant of this integral is always a real number. And another place that you may have seen it is perhaps in Fermat's principle in optics, or yeah, Fermat's principle. Uh, well, all Fermat's principle says is the integral n of x over I'm just going to call this length of x, um, dx. You minimize this, then you sort of, this is a very loose thing to say about, but you minimize this, you extremize this, then you would get the way in which light travels in a setup where light is actually being refracted and so on. And if you've done a bit of analytical mechanics, you might have come across this in Hamilton's principle, in Lagrangian mechanics, and all Hamilton said was, hey, you take this integral that is properly bound between a to b, uh, you know, and you consider t minus v over dt, uh, and you minimize this, you get the equations of motion, and those equations, you solve for them, you can actually show that they're just approximately equal to Newton, but there's more that pops up in field theory, and maybe Prophet can add in here maybe later on. But yeah, this is these are places where you might have seen functionals, but it may not have been mentioned that it's a functional. So yeah, oops. Just a side note before I go about defining a functional rigorously, I'm just going to define what a Lagrangian is. Um, we're going to define the Lagrangian in a broader sense of the term. So this is not the Lagrangian. T minus V is not the Lagrangian for our cases, because this holds when your system is not dissipative, which is to say you're not losing energy over time. Instead, we will define the Lagrangian as follows. So if I have a functional j of x and I am able to express it as a integral over a bounded integral over something like this, the integrand is what I would call the Lagrangian. The term that I'm integrating over is what I would call the Lagrangian from now on. So whenever I mention the word Lagrangian, you must think it's a functional that's expressed as an integral, and the integrand is the Lagrangian. These are more or less equivalent in ideal cases, but we're trying to take a more general approach. This will pay off later, I promise, even though it's a little bit abstract. So this is how I would define the Lagrangian for our use cases. Also, when I was talking about the functionals, I mentioned that I am going to sort of loosely define them first, and then talk about them rigorously. Well, the proper math version of a or the pure math version of a functional is a fun. Whoops. A functional is a map J that's defined as taking V to R for all for all V inside a vector space, which I will talk about in a moment. So it doesn't have to do with functions. It can be just members of any vector space, which is a abstract math object that follows a set of rules. So I'm just going to outline it. It's not really relevant to our discussions, but I thought maybe if I talk about this now, it would pay off later when we're trying to talk about um, groups and so on, because you don't require it when you're talking about Lie groups. But you can think of as when I say functional, when I use the word functional, you can think of it to be a map that takes a function, spits out a real number, or you can think of it as a map that takes a vector, which is an element of a vector space, not just an arrow. I'll define it in a second, and sends it to the real number line. Um, but even before I talk about you know vector spaces, because it's such a absurd word when you first come across it, vectors exist. Why do you need to complicate things? Um, this applies to pretty much any mathematical structure that we're going to talk about later on, groups especially, which will pay off a lot. Any mathematical structure that we talk about is simply a set plus operations plus rules So this is how you should think of it as. So this is the most underlying thing. And how would I define it for you guys? Very naively, without even going too further on, I would just call a set a collection of elements. And it's just some X, Y, Z, whatever. And here your order doesn't matter, and you have your usual, belongs to is a subset of union intersection, yada 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 yada. Really don't want to go into this, but maybe we can later on. But for now, you can take a set to just be a collection of objects. And when you talk about operations, most cases you're going to be talking about something called a binary operation, and it's a very fancy word, but all it means is it takes two inputs and spits out one output, and they're both a part of they're all these three are part of the same set. So it's sort of like a closed operation. So no matter what you do, you take a binary operator and you throw in these. It takes in two elements from the set. The output is definitely going to be a third element that's a part of the set. And again, these operations can be defined within the set, or you can define the set to be a part over a larger set, and then talk about how elements from that set and this set interact. Um, we'll see an example of it right now. And you can also define rules. So you can talk about if they are associ- whoops, associative. Uh, that is to say, if I have ABC, can I actually say, A, B, let's see, whoops, I wrote X. Um, or if they're commutative, which is to say, is A operation B the same as B operation A, and so on. So these are rules. These are rules as to how they interact, and you can also talk about combining multiple different operations. And this is all there is to it. There's obviously going to be some discomfort when you first encounter it. You don't need to remember all of it, first of all. They are rules that we have defined. You don't need to remember them. You can always look them up, is the point. So don't get scared when I'm going to throw in this giant slide uh, right now. And it's a lot. It's a lot to take in, yes. Or you may have seen this before, which is both are equally fine. But all I'm going to talk about is that a vector space or a linear vector space is a set with two operations, addition and multiplication. But the thing is, your multiplication is between two vector elements, two arbitrary vector elements. Yeah, sorry. Your addition is between two arbitrary vector elements, whereas your multiplication usually takes a scalar and a vector. And here, a vector is not an arrow anymore. Rather, it is a member of this set that follows all of these rules. And so when you add two vectors, you say that they need to be commutative to be considered Vector is u plus v is same as v plus u. And I'm just using Dirac notation here so that later on when we're doing some quantum mechanics, you guys are comfortable. But it's just as equivalent to define elements like this. It's the same thing. But I'm using Dirac notation here, which is a rather funky way of doing linear algebra, because the payoff is that it will make quantum mechanics a lot more digestible in terms of notation later on. But you have the freedom to use this as well. Mind you, it's not before I even go here. It's defined over R or C. So your scalars would come from here. Your scalars can be real or complex numbers. Um, so when we're talking about classical systems, your scalars come from R, they're real numbers, and when we're talking about quantum mechanics, they come from C, and we'll see later on why they are so. But you can do just a side note, you can do quantum mechanics over R. It's just that you get a lot of weird things. You get two equations, and it's not standard. That's the point. But this is better. Is- And as a side note, um, these are number systems. So you can ask me, oh, do I really need to define this over a number system? The answer is you can define it over any mathematical object that is a field, a field F. But I'm not going to go into this because I honestly don't like the way it's usually defined, and I prefer it when groups are defined and then we go into fields. But for now, just you can just take R or C. But note that you have a more general case available to you on hand, uh, that all the mathematicians have given us. And maybe I'll just talk a little bit about these guys here. So remember, your alphas, betas, and gammas that you see here your Greek letters come from your R or C, and these these, you know, as I'll call them, kets or vectors, uh, they come from the vector space. So vectors are not arrows anymore; they are rather elements that follow these operations. And one second, someone's phone's ringing. Uh, Apologies, guys. um, okay. Um, but yeah, like so. Ouch. So your addition is commutative. Your addition is associative, and you will always have a additive and multiplicative identity. So additive identity, you add that with any vector, you just get the same vector back. Multiplicative identity, you multiply that scalar by any vector, you get the same number back. Um, so yeah. Um, and you will always have a additive inverse but not a multiplicative inverse, mind you. An additive inverse is simply you add it's like taking -1 and +1 and you just end up with 0. But in this case, your 0 is not just any 0, but it is the additive identity back again. And your multiplication is also associative, and you also have these pretty neat distributive properties. And why was I going through this in the first place? Just to remind you guys that a functional is not just a, a, a function of functions that maps to R, but is rather a function of vectors that maps to R, and vectors are defined as these rules state. And the trick here is that you can then ask me, how are these two definitions equivalent? The thing is, your vector doesn't even need to be some arrow, as I said. It just needs to be something that follows all these rules. And it turns out you can define vector spaces whose elements themselves are functions that follow all of these rules. And they have some interesting things to say about in quantum mechanics and QFT and QG and all of those things. But for our case, this is what a vector space is, and these vectors can be might as well just be uh, functions. And with that, I'll stop. This is all that I used to prepare this talk. Um, and this is the book that I was talking about. Please do have a look at it. I think it's a wonderful book uh, that takes you through this whole thing step by step. And I'll be using physics from Symmetry on the side because it has some really good content on group theory, which I think complements this book because this book doesn't take a very group theoretic approach, whereas this book does. Um, these were other things that I used for images or some cleaner piece of math. I'll stop here, and I think we can start off with questions or comments. Thank you so much for listening.